Dear physics aspirants, right now I have the concept of potential energy, and here you will see the word potential suggests possibility or capacity for action. The term potential energy brings to one's mind stored energy, and here a stretched bowstring possesses potential energy. Here you will see a bowstring when it is released, the arrow flies off at a great speed. The earth crust is not uniform but has discontinuities and dislocations that are called fault lines. These lines in the earth's crust are like the compressed springs. They possess a large amount of potential energy. The earthquake result when these fault lines readjust. Thus, potential energy is the stored energy by virtue of the position or configuration of the body. The body left to itself releases this stored energy in the form of kinetic energy. Let's make our notion of potential energy more concrete form. The gravitational force on ball of mass mg may be treated as constant near the Earth's surface. By near, we imply that height of the H ball above the Earth's surface is very small compared to the Earth's radius. Re is H less than Re, so that we can ignore the variation of G near the Earth's surface. In what follows, we have taken the direction to be positive. Let us raise the ball up to height h, the work done by the external agency against the gravitational force, as mg, as this work gets stored in potential energy, gravitational energy of an object as a function of the height h is denoted by the gravitational force. In raising the object to the height, Vh is equal to mgh. If h is taken as variable, it is easily seen that the gravitational force F equals the negative of the derivative of Vh with respect to h. Thus, F is equal to minus t minus d by dh, and v to vh in is equal to minus mg. The negative sign indicates that the gravitational force is downward. When released, the ball comes down with an increasing speed just before it hits the ground. The speed is given by the kinematic relation v square is 2gh. The equation can be written as half mv square is equal to mgh, which shows that the gravitational potential energy of the object at height h when the object is released manifests itself as kinetic energy of the object on reaching the ground. Physically, the notion of potential energy is applicable only to the class of force where work done against the force gets stored up as energy. When external constraints are removed, it manifests itself as kinetic energy. Mathematically, for simplicity, in one dimension, the potential energy Vx is defined if the force Fx can be written as Fx is equal to minus dV by dx. This implies that I tends to xf fx dx is equal to minus v I tend to vf dv minus form is equal to vi minus vf. The work done by the conservative force, such as the gravity, depends on the initial and the final positions only. In the previous chapter, we have worked on example dealing with the inclined planes. If an object of mass m is released from the top of smooth, frictionless inclined plane of height h, its the speed at bottom is 2gh, irrespective of the angle of inclination. If work done of kinetic energy did depend on other factors such as the velocity and the particular path taken by object, the force would be called non-conservative. The dimension of potential energy are ml square t minus 2, and the unit is joule, the same as kinetic energy or work. To reiterate the change in potential energy for a conservative force, V is equal to negative of the work done by the force. V is equal to minus fx d x 6.9 in this example. In the example of the falling ball considered in the section, we saw how potential energy was converted to kinetic energy. This hints at an important principle of conservation of mechanics, which we now proceed to examine. So, we have discussed the concept of potential energy. In next video, we will discuss conservation of mechanical energy. Thanks for watching the video. Thank you. Thanks a lot.